new batch of people. Some, you know, people that just arrived, like Zeke and Greg is probably already arrived. Allegedly, yes. Javon and a couple other people. So, so the first speaker today is Zeke, and Michael will introduce him because they're buddies, I guess, from old times.
Yeah, tragically for those who were here last week, I don't have any pictures of Zeke running out of gas on the highway. Those are only for Carlos. If you want to see those in the afternoon, I can bring them out again if you missed them the first week. But yep, so I'll be chairing the morning session. Zeke, please begin when you're ready.
Great. Well, first, thanks, Carlos, for organizing this. This is a fun opportunity. And so this is labeled as a tutorial talk. And so I've done my best to sort of put together some slides showing broad scope. But given that mission and given the size of the audience, please interrupt vigorously if you have questions or you want to follow up on any sort of rabbit holes that are interesting to dive down. So I clearly was late in the afternoon when I gave Carlos my abstract. I don't know if anybody bothered to read it. It's quite poetic about how magnetism is both exciting and confusing. The study of molecular-based systems is exactly in that sweet spot, which is, for my personal taste, one of the things that I really enjoy about doing science is just complicated enough to confuse you and just give you a little bit of hope that you can sort it out. So the story I'm going to tell here is one that starts about a decade or so ago for me and getting engaged with these materials, actually longer than that, closer to 2 decades. But so some of it will be historical, some of it will be ahistorical, because one of the through lines through this is trying to develop a new material. So the tutorial talk is going to be very much from the materials perspective, with a focus, though, sort of in the everything old is new again from this quantum information, quantum coherence perspective. What are the new questions that we can ask that give us new perspectives? And so, yeah, then without sort of further preamble, I'm going to talk about 2 case studies, not evenly weighted, much more on the second than the first, but this first category of materials, the Prussian blue analogs, is, I think, arguably the oldest molecular-based magnetic system. The lattice structure here is meant to be somewhat generic. There are not, sometimes, but not always, the purple intercalent atoms, and the red and the yellow are 2 different metal species. In the case of this report, vanadium and chromium. And it's nominally molecular based. You have some carbons and other, I think some nitrogens in there, and you can make these by chemical synthesis. But it still looks, I decided to start here because this looks reassuring from a solid state physics perspective. It still looks like a nice cubic-ish lattice. You can understand, it's complicated, but you can understand where the atoms go. And you get pretty robust magnetism in these systems. So one of the threads that I've woven through the talk, sort of reflecting my experience in the field, is a lot of it is sort of a series of questions that I got when I first started presenting our results in this area. And one of them is like, well, it's anything with the word molecule in it must mean single-digit Kelvin kind of temperatures. No, there's pretty robust room temperature magnetism. Jumping forward to a much more recent result, you can see the similar lattice structure here. It's actually 2 different oxidation states of chromium that are in the lattice. And again, you get sort of nice structural properties, nice DC magnetic properties. But the exciting thing about this recent result, and this is sort of where the quantum Magnonics piece comes in, is if you measure the FMR spectra as a function of frequency, and you look at how on the far left the line width shifts as a function of that frequency, you can extract this infamous alpha. So just realizing I should have put this equation up for those not familiar, but in a Magnonics conference, hopefully everybody has at least seen the LLG equation. And so this is basically the time-dependent trajectory of the magnetization, and there's a phenomenological damping parameter alpha. So Greg Fuchs was mentioned earlier. I'll mention him a bit more. He's a great guy to talk to if you want to dig into exactly what does this alpha mean. That's something he's currently really concerned about. And I will say there's a lot of questions. This is phenomenological. So the microscopic mechanism for this damping is, I think, a pretty exciting frontier for the field. The point is, for those who aren't used to thinking quantitatively about this value of generously mid 10 to the minus 4 is exceptionally low. So one of the things that I often, when talking to new graduate students coming into my group about what we do with magnetism, is that the Hamiltonians have been clear for decades or longer, and the idea of a magnon as an analog to a phonon is not necessarily new. So in some sense, the physics has been there for a long time, but practically, the challenge is in the magnetic materials. And so a more realistic value for alpha for metallic magnets is 10 to the minus 2, something like that. And getting into 10 to the minus 3 requires an enormous amount of work. And there's only one material historically that got into the 10 to the minus 5s. So using this sort of complicated crystal structure, getting into with sort of a molecular basis, and getting this low damping is remarkable. There's really, you can count on one hand the number of materials that can do this. And you can then use that very sharp resonance or long-lived magnons, however you want to think about that, to explore interesting physics. So this paper focused, the motivation for the paper was, I think, thermoelectric. So they were looking at FMR-driven spin pumping, and I'll show on the next slide thermal effects. And so this is sort of well-established spintronics at this point, where you can excite your magnet out of equilibrium, create a population of magnons that generate a chemical potential that drives spin into an adjacent layer, in this case chromium, acting as an inverse spin Hall detector. So that spin current in the presence of spin orbit coupling gives rise to a transverse voltage, which you can use to measure the presence of the FMR. And so this has been studied in lots of magnetic systems, but the size of the signal here is large for a messy system. It sort of goes a bit against expectation. You can do essentially the same physics with a temperature gradient. Again, you're just taking the magnons out of equilibrium. That creates a chemical potential difference, which in the presence of the thermal gradient generates a similar inverse spin Hall signal. You can see here the size of that signal is actually quite large for the field, tens of microvolt. So these exotic systems not only show measurable effects in this regime, but ones that can be large and impactful. So my strategy so far has been sort of easing you in to this concept, because the next material system I'm going to present does even better with even less intuitive underpinnings. But yes. Oh, should we be miking it?
Yeah, thank you. I have a very naive question. So can you give me a flavor which of these materials are conducting and which are non-conducting?
Sorry, yes, I was sort of breezing through this.
Or I might have missed it. So
No, I didn't bring that up at all. This was, yeah. So the magnetic material here is generally not a good conductor. So the transfer across the interface, and I don't know, maybe this diagram's a little easier to see. So the interaction at this interface is a pure spin-spin interaction. It's an exchange coupling between the magnons on the one side and the conduction electrons in the conductor on the other side. You can do it with a metallic magnet, and that has given rise to endless PRLs analyzing artifacts and trying to disentangle what's happening. So yttrium iron garnet is with asking Georg's pardon is the villain of this story, right? Because yttrium iron garnet is the canonical system that does this extremely well. It's highly insulating. It has very sharp magnon resonances. So it gets rid of most but not all potential artifacts. And so this Prussian blue analog is sort of taking the role of YIG in a sort of more conventional all inorganic structure. Yeah. So is that cover what you were interested in?
Yeah, but since the tutorial and you're about to shift to another material, let's see if there are any questions at this point, particularly about the Prussian blue. I certainly have one. It's the obnoxious one, which is, so Zeke, what is the saturation magnetization of this material?
I actually checked for that. They didn't quote it directly, and I ran out of time to extract it. But you can sort of ballpark it from the hysteresis curve, the saturation curve. So this is not exactly quantitative, but basically around the field at which it saturates. This is proportional to the saturation magnetization with some coefficients out front. So it's in the ballpark of 100 millitesla or 1,000 Gauss, or if you prefer those units.
And that has generated some questions. Jörg.
I would simply like to comment on something which may also be a link to my talk. If you could go back to the damping. It is remarkable that you have 7.5 times 10 to the minus 4, but it's also remarkable that the line width changes by 3 Ørsted, but it is already at 260. So that means this is extremely inhomogeneous material.
Yes, that's. Thank you. I had meant to point that out. It's also a nice segue to the second piece, and I think. Let's see, is this in here? Well, no, I didn't include that figure. But the way that this is produced is an electrochemical effect. So they essentially put a chromium film into a wet solution and sort of do electrochemistry to build the Prussian blue structure on top of it. So very chemistry forward approach, which is great for materials discovery. And as you can see, is pointing at some really exciting potential properties here, but is not great at uniformity. And so I'll sort of fill in this story as we go through the talk, but in many ways, my personal engagement with the field is coming from a background in physics, thin film epitaxy, sort of very, very pure, very carefully controlled materials development, and interfacing with the chemists who pioneered this field, sort of established that this material existed and had promising properties, but then, okay, but how do we move it forward and optimize it in a way that allows us to do fundamental materials? And exactly to this point, and this is a sort of a subtle one when thinking about Magnonics, is sometimes you care about the damping, sometimes you care about the absolute line width, sometimes you care about both, and those are various constraints. So I think because of this electro deposition synthesis technique, the film is, I'm sure, massively polycrystalline and with some rough morphology and whatnot, which I'm sure is contributing to that extremely large inhomogeneity. It's an excellent point. We're moving on? We're moving on. Okay, so jumping back to 91, this is sort of the foundational paper for the material that I want to spend most of the time talking about. This is vanadium tetracyanoethylene, or VTCNE. So this is progressively less comfortable for a physics audience because the molecular piece is now significant. You can think of it as a binary crystal structure where instead of two atoms, the second atom is replaced by this TC&E small molecule. But it's still maintaining its molecular character. It's not just one or two carbon and nitrogen atoms thrown into the lattice. And I'll come back to the structure in a bit, because one of the stories of developing this material is that it's taken quite a long time to get a handle on what that structure actually is for various technical and fundamental reasons. But in this initial demonstration, the key point here is the temperature scale again goes up to room temperature. This temperature dependence is very strange. I wouldn't spend too much time worrying about the fact that it's linear. I think this is again a sign of disorder. This was a solution, pure solution chemistry, so synthesizing a powder, but you can see still showing very, very nice saturation, very clean hysteresis. Coming back to my earlier point, if we want to just start off with ballparking the saturation magnetization, building off Michael's foreshadowing, and we've now changed units, so this is Oersted. So the saturation magnetization was out here for the Prussian blue. It is significantly lower field for this VTC&E. So this was the initial discovery. Joel Miller, a chemist at the University of Utah, and Art Epstein, a physicist at Ohio State, which is how I came to find out about this material. About a decade later, they, in continuing to work with the material, they made, I think, one of the critical advances for the utility of this system, which is moving from solution synthesis to CVD, chemical vapor deposition growth. So this is a pretty simple setup because the deposition conditions here are quite mild. The pressure is a couple of torr of argon or nitrogen. The temperature is about 60 C, so that means this can all be glass, and you flow two precursors in. The TC&E, as I mentioned before, maintains its molecular character, so it is its own precursor. The vanadium is a little more complicated. The precursor there is vanadium hexacarbonyl, VCO6, which decomposes when it reacts with the TC&E to form your solid. And I'll say this is the reason why this material is not more widely measured. It's unstable and pyrophoric and incredibly challenging to synthesize. So you're not going to find many chemists who have a vial of this sitting in their glove box. That being said, it's possible to sort it and get it systematic. But the main point being, coming back again to this this temperature dependence, again well over room temperature. These black triangles are extrapolation of the saturation magnetization from the hysteresis from high field values, and then these two curves are the field cooled and zero field cooled of the thin film. And I'll point out that measuring the Curie temperature here is a little bit tricky. I mentioned the deposition temperature is about 60 degrees Celsius, and just sort of generally from a materials perspective, that tells you about how hot a material can be before it starts to decompose. So you'll notice that's suspiciously close to the transition temperature here, and the shape of this curve doesn't really look like a magnetic transition. I have a long-running debate with Joel Miller about this, but I would say this is a structural decomposition, if you want to call that, a magnetic transition when you vaporize your sample. That's fine. It's phenomenologically the critical temperature. Actually, I think in the next slide, so I'll just do that. So this is work that my group started in collaboration with Arts in optimizing this thin film process. And you can see the M versus T looks quite different in the more optimized film. And here I'm quoting a Curie temperature of 600 Kelvin. So we can't measure the sample anywhere close to 600 Kelvin without it turning into soot. But if we take what I would consider a more physics perspective as opposed to a phenomenological perspective on what TC means. Just take that as an energy scale associated with the magnetism in the system. Then you can sort of fit that high temperature region to a block law and say, okay, well, where would I predict that to hit the axis? And you get something of about 600 Kelvin. So, and then on the right, just using that transition temperature as a crude metric of materials quality, you can see that starting from the solution synthesis, which gives you a powder, then transitioning to CVD, that first open square is the previous slide, and then progressively optimizing the material coming from, again, a thin film growth perspective, you can get significant improvement in homogeneity and materials quality. And so this has been sort of one view of the trajectory of this system. So let's discover together what my next slide is. That's what I thought. So this is really the question that I started getting as soon as I started working with Art on this material and talking about our results. I, in the end, didn't drop any slides in, but for fans of the genre, our first paper was a spin LED measurement where you use VTC&E as an electrical spin injector into a light emitting diode and use the polarization of the light to measure the spin polarization. And we got that to work surprisingly in this molecular-based system, which shouldn't really be magnetic, at a heterointerface that should have been much harder to engineer, yet still somehow functioned. And when I went to give this seminar in front of physics audiences, I would get this question a lot. Why does this work? This should not work. For many reasons, but I think the one that people are working with solid-state magnetism are primarily concerned with is there's an enormously long distance between vanadium spins, according to most common heuristics of what makes a good magnet. Right, so that's 6 atoms between vanadium to vanadium if you sort of walk your way through the TC&E molecule. And it's not unheard of to have magnetic interactions over that distance. It's shocking to have a 600 Kelvin ordering temperature with spins that are that far removed. And so this was, the story of the beginning of my, my pre-tenure through early tenured faculty career was giving talks about this and having people ask me this question and me say, I don't really know. It's a great question. We're working on it. There are properties of this system, which I'll get to in a second, which make it well worth exploring even before we have that fundamental understanding. But now I'm going to pivot to the somewhat ahistorical part of this talk where I'm going to jump ahead to give some recent results that I think shed some light on how we address this. So this is sort of an idealized crystal structure, sort of stepping your way down. So obviously from like a full crystal, zooming in, and then I'll come back to this picture in a minute. This is roughly the same scale, but moving to sort of a vanadium-centric picture. So this is bigger than 1 unit cell on the right, but I think that's sort of the most intuitive way to understand how the structure looks at the atomic scale, as we have a vanadium with 6 TC&Es coming off of it. So you have that octahedral coordination locally. So we're not doing true, real single crystal growth. So the material's highly disordered. So the way I think of it is it's polycrystalline with a grain size that's quite small. We're still trying to figure out how to get good measurements of exactly how small is. 1 to 10 nanometers would be my guess. But just to sort of set expectations. That being said, this model and this understanding can tell us a lot about the material's properties. And so working with Michael's group and David McComb at Ohio State, who's a TEM microscopist doing electron energy loss studies, we were able to develop this picture of what the electronic structure actually looks like. And what we discovered is that not all TC&Es are created equal. So there are 4 in plane equatorial TC&Es, and then 2 apical, sort of vertically stacking TC&Es. And if you look, if you think about the stoichiometry of vanadium TC&E2, what that means is that not all of these terminal cyano groups, so I should have explicitly said this, the yellow here are carbon, the grays are nitrogen. It's the nitrogen that are directly bonding to the vanadium, which is a pretty strong metal bond. But not all of these terminal cyano groups get a vanadium. Every vanadium is fully coordinated, but not every TC&E is fully coordinated. And so the equatorial TC&E all talk to another vanadium. So you form sort of a sheet of vanadium and TC&E, but then the bridging between those sheets, we have these apical TC&E, which only have 2 of their cyano groups coordinated. So, these diagonal cyano groups, on average, basically if we were to form a perfect crystal, don't have any coordination here. And so that does a lot of interesting things, which I'm sort of diagramming on the right here. So this is a spin-resolved density of states, and with apologies to Michael and his crew, I'm picking the cartoon version because it's easier to point at. I'll show the actual calculations in a minute. They actually did do all this work. But the first is that it's spin resolved and sort of matching color to color. These are the 2 pi star orbitals on the TC&E. And so you can see first there's this poly splitting that's huge. It's 2 eV. So that's what the interaction that's driving, or one of the key interactions that's driving the magnetism and the spin polarization in this system. The other is the difference between equatorial and apical. You can see that also is a pretty large energy scale. So these different TC&E groups are behaving very differently. And this would lead in sort of, if I want to use the language of magnetism, this would lead me to expect some strong crystal field interactions, basically some crystalline anisotropy in the system, which we have observed. So this is fully consistent. And then the red states are the vanadium d orbital, and I should have mentioned earlier this is a Ferri magnet. So we have spin up on the central vanadium of 3 halves, and then spin down of 1/2 on the TC&Es, which the stoichiometry gives you a net excess moment of spin 1/2 for the unit cell. And then this red box is defining the band gap, which is indirect in spin space. So this is a fully spin polarized organic semiconductor, if you want to think of it that way, or a half semiconductor if you want to borrow from the half metal community. So this is a pretty remarkable density of states. There's just not many materials that look like this, and I think that this is part of the reason why we're able to see the properties that we observe. So let me pause here because I'm about to dive into the data, but this is sort of just starting with an orientation for the crystal structure. Yeah, Carlos, did you have a question? Or?
Yeah, just a standard question. The gap in DFT. Do they do anything to this when they do the calculation? Like, you know what I'm talking about. Like,
fortunately, we have my collaborator in the room to answer that one.
So I think what you're pointing to is the challenge that you often have with the band gaps, particularly of semiconductors. So there are a few wrinkles here. One is that the main issue with typical semiconductors is that their mass is very light, and that means that small errors can balloon in terms of the band gap. So the mass here is quite heavy, so that means that it's much less susceptible to it. You can do the standard things. You can do the calculations with and without U. You can do hybrid calculations with the standard mixing parameters, and they all take you towards this 0.7 EV band gap, which is relatively robust. But unlike something like gallium arsenide, where you might get a 0.7 EV band gap if you do kind of a straight calculation, and its real band gap is 1.5. Here, the shift is a lot less, just because of this issue that the mass of the carriers here is so high.
And Carlos, as ever being a thoughtful host, is a perfect segue to my next slide, where I show the integrated density of states from the DFT, as well as energy loss from the electron microscopy. And there's some dielectric modeling that one needs to do in various things. Oh, did I say the wrong thing with density of states?
Yes, that is actually what it shows there, which is 1 over the dielectric function. So
Sorry.
it does include the matrix elements. So, sorry.
Yeah, sorry. Yes, sorry. That's the spirit of what I was saying with completely butchered language, which I apologize for.
And
But-
theoretical obsession.
The bottom line is we start from the DFT calculation of the density of states, then sort of apply the appropriate physics to imagine how that compares to the experimental observable, which is effectively the dielectric function, and find extraordinarily good agreement, including with the band gap. And so there are a lot of phenomenological aspects of the experimental measurement. So I wouldn't take the amplitudes of these different curves too much to heart. It's more the energy alignment of where the various states exist. And we find quantitative agreement that's shockingly good, I would say, for this kind of comparison. So just again, to give a bit of the historical perspective, this paper came out in 2022. So I was working in this field for close to a decade, where people were asking me for this picture because that's sort of the natural place to start in understanding a new system. Well, what's the crystal structure? What's the electronic structure look like? And really it was not understood in the field how this was working. There was 1 or 2 prior pieces of DFT, but not with any direct connection to experiment. So this smoking gun was really transformative in our ability to understand this system and sort of to foreshadow a bit, to give us the confidence that we were in fact observing a representative of an entire category of magnetic materials that I think has been substantially underexplored, but with a lot of potential excitement for the quantum regime. So this takes me back to the question of why does this work, and this is a little bit hand wavy, but so this is a measurement of spin density just in TC&E, just in the bare molecule, and what this is effectively representing is sort of the molecular orbital of the pi star electrons, the pi star orbital and the TC&E that lives predominantly in the carbon-carbon double bond in that backbone structure, but hybridizes out strongly out to the nitrogens at the end. So that means that this same counting of 6 atoms between the 2 vanadium, this is where our heuristic led us astray. If we're thinking of sort of a traditional solid state material, that feels like a long distance because you're hopping from atom to atom to atom. The fact that the TC&E is retaining some of its molecular character means that there is a delocalized molecular orbital that extends over the entire small molecule. So it's really more a next nearest neighbor type interaction, that we can really think of this molecule as an artificial atom, right? Which is a phrase that the quantum dot community coined, but I think translates reasonably well into this picture. So this is my first explanation of why we can have such strong exchange coupling leading to high temperature magnetic ordering in a sample in a material where the spins are so far apart. Okay, so another question I get a lot from physicists, and actually critically for the field from chemists who have been traumatized from talking to physicists. Not that physicists aren't warm and cuddly. I can't imagine what sort of interaction they had that would have driven this. But working with a system like this, the question is, well, but is it stable? And it's not in air. And so that limits potentially the applications, right? It's not neodymium iron boron. But can we make it stable, or what are the mechanisms of degradation? The electron energy loss provides insight there as well. And so this is stability measured, or degradation measured on two different axes. So here, the blue curve represents a sample that's transferred essentially in air, or essentially unperturbed from the growth chamber into the TEM and measured, and focusing on this sharp spike on the low energy side, and this peak here associated with the carbon. As soon as you, and then the orange curve is what happens when you sort of leak some oxygen into the chamber before measuring. And you can see dramatic changes in the carbon lines, but not much change in the nitrogen line. So this is a little surprising, because if you were to ask me what happens when this material oxidizes, well, vanadium oxide's incredibly stable, common compound. I would assume that's where the oxygen's going. In fact, it's attacking the carbon-carbon double bond. So that's where oxidation happens. That's one failure mode. So we need to protect this from air, but we know how to do vacuum packaging and encapsulation and various other strategies. So that's not actually that much of a deal breaker. Also interesting is what happens if we let it age in the absence of air. And so this is a bit subtle, but if we look again at the blue curve is sort of the best data, you can see most clearly on this vanadium peak that there's this shoulder, and that shoulder is representative of high quality octahedral symmetry. And what happens is over time, or with oxidation, that shoulder relaxes, which tells us that that octahedron is starting to distort. So what this is telling us is don't let it see air. That's bad. But even if you protect it from air, there's still some structural relaxation that takes place over longer periods. And so there's fun material synthesis things that I can dive into there, but I want to focus. That's not necessarily the focus of this tutorial, so I'll leave it at that. But the main message is that it does still age out if stored at room temperature on the time scale of about a month. And while that's not great in itself, it does point to interesting directions to improving the material, looking for other materials that don't have that effect. That being said, if you keep it cold and air-free, it's good for forever to first order. We can also see evidence of this in Raman measurements. So these are measurements coming out of Greg Fuchs' lab, and you can see again the carbon double bond and the carbon nitrogen bond on the end both have identified Raman modes, which again the DFT model that we now have allows us to calculate and compares, I think, pretty well. And when I say promise for future stability, so this is a sample we had sitting in our dry box for 5 years. And you can see it started to oxidize a bit from the edge, but sort of self-limited. The black at the top is the color of as-grown VTC&E. And that sample looks pretty much the same as when we grew it. The magnetism has degraded, but the Raman character has not. So there's some structural transformation that's happening over time, and you can see stability, sort of years, days, it basically all does the same thing. So there's something happening with a structural relaxation that over long time at high temperature, presumably this is sort of annealing. Like remembering room temperature is quite hot for this material system, right? It deposits at only 60 C. So, so that's, again, if you're a pessimist, one boundary condition, don't put this don't use this sample for like, or this material for building sensors that you're going to put next to a jet engine. But more optimistically for the science, it suggests that if we tweak this, if this really is a class of materials, that there's likely changes we can make to address this relaxation and perhaps get more long-lived magnetism. That being said, it's still pretty long-lived. We can dig into this if people have questions, but just focusing on the red data, which is 4 pi ms, or M effective, if you will, from FMR measurements. This is a log scale, but that's still pretty flat on the time scale of a month. So we're in pretty good shape. So I realize, this is the point in the talk when I realize I dramatically over-prepared in terms of the number of slides. So I'm gonna start hitting the gas a bit here. But this is appropriate because I also have a research talk coming up where I can recycle some of this and we can ask more questions. But so I think that intro of sort of the foundation of how this material works is where what I really wanted to get across. And then pivoting now to why am I here in a quantum magnonics workshop, given that was a very materials intensive introduction. And you can see that here. So I mentioned earlier that the Prussian blue has a damping parameter of 10 to the minus 4. Good but not exceptional VTC&E films have mid 10 to the minus 5. YIG is the only other material that does this. This still astonishes me, honestly, in both directions. I mean, there's to date 2 materials ever discovered that have magnon damping this low. So that's exciting. And Georg and I can have an arm wrestling contest about whether YIG or VTC&E outperforms on any specific metric. The bottom line, I would say, is they're comparable and complementary in many ways. And as I'll say in a moment, for device integration, there's some pathways opened up by the VTC&E material that are particularly exciting. In particular, because again, coming back to the CVD synthesis, it's such a gentle process, low temperature, modest pressure. We can use e-beam lithography to pattern and lift off the deposition. So that means we can form arbitrary structures. But interestingly, the growth dynamics are not UHV sort of direct beam deposition, but rather convection flow, driven by the gas dynamics, and effectively you form a vortex at the edges of your pattern where the diameter of the vortex is basically the height of your resist layer, and that leads to this sort of lens-like cross-section. Some combination of that and the fact that we're not etching and cutting sidewalls, introducing damage, means that when we make these patterns, and I'm realizing now I didn't put that data set in, but take my word for it, or you can check the reference, that introduces no additional damping. So this is unprecedented in magnetic materials. So not only can we get very low damping magnons, we can pattern them without any subsequent annealing or modification steps in a way that preserves that ultra low loss. This is just sort of zooming, giving everybody the chance to actually see what's in this complex compilation here. And this is just sort of talking about the flexibility that this gives us. So the way I like to think of this is we can make magnon resonators with sort of arbitrary shape with control over anisotropies. Here is the in-plane to out-of-plane angle dependence of FMR for bars and disks. You can use this to extract the anisotropy parameters that take shape and crystal field into account very exactly. Those parameters then should fully predict the magnon spectrum of the material, and in fact they do. So I'll get to the second. There's an analytic calculation in a second. This is a numerical calculation using mumax, which is The green arrows represent sort of Magnon modes that are exactly reflected in this blue experimental data, match the simulation quite well, using no adjustable parameters in the simulation, just the parameters extracted from the angle-dependent FMR and the anisotropy. And the nice thing about the MuMax is then we can use that to develop sort of maps. So this is of a model of a disk where we've approximated the lens-shaped cross-section just with a linear. And the color scale is the phase of the magnetization. So that's maybe easiest to see in the n equals 0 and the n equals 7 state, where you have sort of boundary conditions for the n equals 0 state, but basically you see the magnetization rotate once as we go vertically through the structure, rotate many times for the n equals 7 Magnon mode, and we have effectively thickness quantization with slight modification from the radial direction, because these are still relatively large structures, but that's what gives it, like the n equals 3, n equals 5, this kind of more complicated approach is because we're having some interaction between those things. The bottom line being here, we can make Taylor-ordered Magnon resonators. I think that's really what we were excited about with this demonstration. So for quantum magnonics, you can imagine that's exciting. This also comes with another mystery, though, and this is, in fact, sufficiently mysterious that at least I didn't fully realize this was surprising for a couple of years working with the system. So this is now zooming in on the experimental data in blue, and you can see these very clear Magnon resonances. We fit out to 7, but you can see there's likely even more excited state, complex higher order behavior there. And those black dots represent analytic calculations of where the thickness quantized spin waves should lie. So the agreement's quite good, and you can use that to extract an exchange stiffness for the spin wave. Basically, how much energy does it cost to rotate my spin as I move along the wavelength of the Magnon? And so we can extract that number. Then there are a number of heuristics that link AX, the exchange stiffness, to the M sub S, the saturation magnetization, and therefore you can use that to predict the magnetic ordering temperature, and we get 10 Kelvin, right? Which in one sense is reassuring for skeptics in the audience who, on seeing the crystal structure at first, said that should not be a good magnet. This would argue, yeah, it's not a very good magnet in the sense of being strongly ordered, but that's in direct contradiction to the experimental observation of the high TC. So why does this work? It requires a little bit of thinking about what M sub S actually is. So the way it's commonly defined in these heuristics from the previous slide is its volume normalized spin density over the volume of the unit cell. So it's intrinsic. It's not volume normalized in that sense, varying sample to sample, but it does depend on the size of the unit cell, and VTC&E crystal structure is incredibly porous. I'll say more about that at the very end of my talk. But what that means is that we have very strong exchange coupling where there is material, right? So that's a large energy scale for the spin alignment in this direction, but the overall spin volume is quite small. Coming back to Michael's question about the saturation magnetization, typically we get 50 to 100 Gauss saturation for VTC&E, which is, I'm blanking on the number, but at least a factor of 10 smaller than YIG, which is already considered to be a relatively small MS in the community of magnets. So I think this is, if not quite a complete model, a smoking gun pointing at why we can have these, very nice Magnon properties in the system, is because the molecular nature allows us to find this regime where exchange is strong and MS is small. And so I guess in the spirit of the tutorial, like the the other comment I would make here in terms of thinking of directions for future work, a lot of magnetism that feels well settled is in fact only well settled given certain assumptions about sort of what regime of phase space we're in. And those are very reasonable assumptions because, again, as I said earlier, magnetism and certainly magnetization dynamics is strongly materials limited. All the materials we had access to were in one corner of phase space. This is a very different place. And so I think that opens up a lot of possibility. So I have 10 minutes left, so I'm just gonna quickly throw these guys up. We can circle back. I'll try and leave as much time for questions, but we can do self-templated patterning, again, using Mumax for the color contrast to show the spin wave spectra. If we do the angle-dependent FMR, we can vary the coupling between different magnon modes within that complex structure, and in fact can see very clear anti-crossing between magnon modes. So I'll call this like the strong magnon-magnon coupling regime. So that's a fun place to engineer and look for new problems. The material itself has a combination of very sharp resonance with reasonably strong coupling to strain. And so in the bottom right corner, you can see this depositing BTC&E on top of a piezoelectric material. We can intentionally strain it in a way that gives us, let's see, did I write that down? I did not write that down. So we can define a figure of merit for magnetostriction. That's not, the traditional figure of merit is how far does it move per strain, which is an important number. But practically, it's how many line widths does it move. And so by that measure, this is as good a material as galphanol, which if you're not familiar with the field, that's sort of the gold standard magnetostrictive material. So that means for a lot of applications, we can move by, so this is about 6 line widths at maximum tuning. We can very clearly separate resonances and tune them, which is exciting capability. Similar to the Prussian blue, we also have been able to measure the Spen-Zabek effect in VTC&E, and this is work that Dennis Candido led the theoretical development. So he's around to ask all the hard questions of. And I'll just say that again, because of this extremely low damping, VTC&E gives similar performance metrics to YIG, and the longer story, which I don't have time for, in the right there is that this combination of strong exchange and low MS puts us in an odd regime for optimizing the Spen-Zabek effect, where normally you would want a large magnetization. It has a very small magnetization, but that couples to the low damping in ways that are interesting in tuning the magnon band structure to effectively circle around and end up with numbers that are comparable to YIG. Similar for FMR-driven spin pumping. So Greg's talk later in this workshop will focus a lot on this. So I just have one slide, but again, this is the payoff. This is why I dragged you through all the materials stuff. We can deposit VTC&E directly on top of a superconducting resonator without perturbing the circuit, and get into this strong or potentially ultra strong coupling limit for magnon photon coupling, which is a really interesting direction for quantum technologies. And then again, I think I saw in Dennis's abstract that he may mention something about this. If not, feel free to track him down. But using the dipole fields generated by these magnons, you can also imagine coupling to paramagnetic spins. And spin magnon coupling with high cooperativity is also, I think, a very reasonable target for this field. So I will skip through most of this, but I'll say just to justify a broader class of materials, you can vary the metal ligand or the metal atom. That's been done in solution phase, has not been optimized by CVD. And if you remember that curve I showed about the change in properties moving from initial chemical wet synthesis to optimized thin film growth can show significant improvement in properties. So this is something to keep an eye on, especially because room temperature is not so important for quantum technologies. Everything has to be cold anyway. You can also change the ligand, which we have looked at in the CVD regime, and the DC magnetic properties are interesting. We're varying both the electronegativity and the bulkiness of the ligand, as you can see in the cartoon up here. So it's not so straightforward from this one study to disentangle these two effects, but you can make what I called at the time the second best molecular-based ferromagnet, which is to say it still has room temperature ordering. You see this characteristic peak structure at like 150 Kelvin. That points to some interesting physics in the underlying magnetic ordering. But the last thing I want to mention is just come back to this porosity, and our collaborators in the Long group at Berkeley have done sort of a gas adsorption measurement where you take these various gases, you increase the pressure, you see how much of the gas gets absorbed or adsorbed into the porous structure, and you can use that to calculate a pore size of 9.7 angstroms, which didn't mean anything to me as a number, but in talking to the chemists, they got very excited about it because that's a porosity comparable to zeolites. So people, if you're not familiar with that class of materials, that's what people generally use as a gold standard for highly porous materials for sort of gas storage and filtering and cleaning. So just to say these are incredibly porous, which then opens another direction for materials development of potentially manipulating the magnetism, the magnons, perhaps even in situ with dynamic control by intercalating atoms, molecules, other sort of materials within the VTC&E host. And so I will stop there with a whole like 3 minutes for questions, but we have plenty of discussion time later in the meeting.
Questions?
Thanks, Zeke. Very nice talk. So I have a question related to this last part. More specifically, if we could, like in the last week, we discussed like magnons as a sensor through if the magnum bands coupled through whatever, you can experience, infer what you're coupling to. And so here I'm just like wondering whether VTC&E could also be used as like a gas sensor, because you know different gases are going to modify the saturation, magnetization, Curie temperature, and etc. And just like wondering if you guys are looking into this direction.
Yeah, so I think VTC&E itself, not because of the oxygen sensitivity. So if there's a use case out there for measuring gases that are not oxygen in a sealed environment, then yes, exactly this material. I'm not aware of one, but one of the other things we're doing in the direction of alternate ligands, and this work is still in development, so I didn't put a slide on it, but the Long group has identified an additional ligand to replace the TC&E that promises much better stability and perhaps even higher porosity. So when I'm talking about sort of the class of materials, I think it's very plausible that there is a material system out there that can do the kind of thing that you're saying.
Thanks for the talk. This is very interesting. Maybe you mentioned it, but or maybe you left it as a pure mystery. But is there any reasonable explanation for how it is you can get an exchange stiffness that gives you a TC of 10 Kelvin, and then think of some alternate theory that still gives you this transition temperature that you measure?
I don't know if I would dignify it with the label of theory. So it's a bit hand wavy, but this is sort of what I was trying to allude to here, is that you have an electron, a single electron state that's highly delocalized across that red line. So that leads to very strong next nearest neighbor exchange coupling, or antiferromagnetic exchange between 3/2 vanadium minus 1/2 TC&E, 3/2 vanadium.
Okay.
So the energy scale along that direction is very high. And so that order is going to be quite robust. But then the magnons interact through both exchange and dipole fields.
Sure.
And so they care about the total volume density of the spin. And these large pores strongly suppress that volume density, which means that sort of the exchange stiffness, basically how easy is it to rotate adjacent spins as you move down the line is quite floppy, because the spins are moving into this empty space with no other spins to push back against them. So I think it maybe one way to say it, I can't remember who off the top of my head.
So if I think of a pure Heisenberg ferromagnet, they're the same thing, right? So you're saying there's a different type of...
Could I'll take another shot at this, which is the exchange stiffness has a volume component to it, right? So it's essentially a continuum model where you've smeared everything out evenly over the system, and that's a total failure for this, because the spin active regions are maybe 100 times smaller in volume than the total volume in the unit cell. And so what you should use is sort of the volume that's well occupied by electron density. And if you were to use that kind of thing, then you would get a much higher effective number.
No, I have a question related to that. So if I follow up on your trajectory, so would you say that I should expect a highly anisotropic damping, depending on the magnetization orientation, how I prepare it in this crystal? And isn't it just the anisotropy?
Yeah, so that sort of
disentangles
depends on the
those?
spin-orbit interaction and how it plays. And in this situation, the only spin-orbit interaction is on the vanadium, which has a pretty highly symmetric coordination. There's essentially no spin-orbit interaction on the TC&E. So sort of operationally, it seems like it's not anisotropic, and it probably wouldn't be anisotropic.
Okay, may I have the second one? So I'm now coming from this kind of purely applied engineering character. So you have a system with exquisite Gilbert damping. If you want to do anything realistically quantum with it, what are the typical properties we're looking for? Kind of absolute line widths, I would suggest. Also in terms of the beautiful spatially resolved Magnon patterns that you have showed. It's about the effective propagation lengths that the magnons can have. So if you factor in group velocity, phase velocity with lifetime. So can you give us some numbers on this in terms of, can I propagate information in these systems? And then also the additional question would be mechanical properties. So what are the mechanical properties of these materials?
So I might need your help in stepping back through that as I go through to make sure I don't miss something. But
Propagation length of magnons in the material, I think, was the key thing.
yeah, and that is actually short. So I think using the magnetic material as an interconnect may not be the best application here. I think, and so far this is based on modeling coming out of the Spenzabek work, so we haven't measured it directly yet, but I think reasonable level of confidence that what we're seeing is that the lifetime of the magnons may in fact be longer than YIG, but the propagation length is shorter, and those effects cancel out to give roughly comparable sort of diffusivity. But in terms of the coherent propagation that you'd want to do for very long distances, it's not clear the magnons have very long range. I don't know, Mike. collaborators may have a different take on that.
So essentially, the spin wave velocity is a lot smaller than it would
Yeah.
be in YIG.
Yeah.
And that's sort of related to that exchange stiffness. And so the distance is not as long. But
Right.
And maybe it's kind of a follow-up question would be, how large a structure do you see quantized modes in, which sort of gives you an idea of the
Okay,
scale.
let me put a pin on that to add one layer to my first answer, because you also mentioned sort of the spatial patterns for the mode engineering. So explicitly, that spatial control I take it back. So that's not the goal in terms of long distance propagation. It's just more, you can engineer the resonance frequency of the modes, for example, which has value. Engineering the spatial mode, and this touches on Michael's question. Let's see, is this here? Here. So, and this is work that Dennis really drove. You can imagine sort of engineering a microstructure such that it has a whispering gallery-like mode, for example, which you can effectively engineer to enhance this spin-magnon coupling. So it's that kind of control that I think has the application for quantum. And then Michael's question about the size scale of the quantization is, I would say, about 100 nanometers is when that starts to be interesting. So like in the thickness modes, the films that I've been talking about are about 400 nanometers. So disks in the microns range, you can start to get really substantial radial quantization out to 10 microns or more or ish. You can use that as a perturbation, maybe for fine tuning, for that kind of thing. We haven't really pushed short range patterning yet. We just haven't had a reason to push hard on that. But I think that there's a lot of space for development there. So I don't know if I got to all your questions, or Michael, did you have a follow up on what I was just saying?
No, I was just going to ask if there was one other quick question before. Are you quick?
Well, actually, the schedule is quite flexible. We have a coffee break now. We usually shift a little bit things over, because after the next talk, there's also some time for discussion. So we do not really have to stop we not have to be too strict. Could you go back to that picture where you have the density of states, the theoretical, your sketch? Yeah. Is it true that, if I look at this, the spin splitting, or you call it Pauli spin, splitting, or that's exchange splitting, you mean, right? So is it, if I look at the several, for instance, for the empty part, is it different? This UP varies, right, as you go from, or it's the same? So it's just a sketch then? So why is it constant? Should they expect it to change?
Well, I think these are both pi star electrons. Is that right, Michael? Like occupied and unoccupied.
Mm-hmm.
So they're effectively in the same orbital. So I would expect them to generally, I mean, not every excited state would be the same, but I think they're.
And up there? Well, if it's a sketch time, but it looks like it's not, is it? This?
You're saying, why don't we have something that's kind of...
Yeah, for instance, between the, this.
What I would say is that this is a sketch that's extracted from the calculated density of states, and it takes a little bit of inference to disentangle. And it's a little hard once you get into these sort of conduction states to really identify clearly. You have more of a broad, you have less features because it's higher energy, so there are more states with different orbital character that they can go into. It's not, the sketch is sort of failing as the bandwidth increases as you go higher in energy.
And experimentally, can you probe this?
Well, so for a bit, right? So we see resonances at 5 and 6 eV, so we can get into that range. You, in principle, could spin resolve this. So this is electron energy loss. If you did spin resolved electron energy loss, you might be able to see that effect. I think that's a challenging experiment. That's I think a beamline style experiment, but is potentially possible.
All right, Dennis.
Just one more question related to the porous character of the VTCNE. I would like to know if you could comment further on the avenues that having this porosity can open for integrating with qubits, like the molecular qubits. So yeah, I know you have been working on this, so I just would like you to kind of like give us a little bit of an overview on your thoughts on this.
So the model I've been working with and imagining how this system might function is to think of sort of the cavity QED with atoms in an optical resonator. And in our case, we would then have, rather than photons, have magnons coupling to intercalated spins that would be the quantum system. So this would be necessarily an ensemble regime. We're not going to put a single intercalant in, although, well, that's very fun to think about. I don't have an experimental avenue on that just now, but you could imagine having a modest ensemble, I don't call it hundreds of intercalated spins within, say, a 1 micron to 10 micron Magnon resonator. Use the Magnon mode to drive the coherence among these paramagnetic spins, right? So you can do similar sort of ensemble quantum information type studies in that regime. And then, as long as I'm building castles in the sky, and I can find a chemist sufficiently motivated to build in interesting functionality to those qubits for readout or for function, there's maybe some directions to pursue there. And then I think a related direction is we can also set aside the assumption of interesting quantum functionality directly in the intercalant and use the intercalant to modify the Magnon functionality. So for example, if I have a small molecule that docks somewhere in that void, and then I can apply an electric field, for example, to perturb it and kick it from one state to another. And here, this is sort of loosely inspired by the hybrid perovskite structures, where you can have the small molecules in there, have some dynamics that are visible in certain regimes, that might be an interesting way to think about modifying the Magnon spectra by electric field control or other things like that.
All right, other questions?
This might be more a question for Michael, depending on how it goes. But so do you know much about where the spin density lives in these bands? So you can look at pictures of the spin density. Is it all in the vanadium, or does it spread out?
Well, yeah, so this is for pure TCNE.
And how accurate is this in the material? I guess that's the question. Because if you put the vanadium in there, the vanadium is the magnetic.
Well, but it's a ferri magnet.
Okay.
So the vanadium comes in and it donates an electron to ionize the TCNE. So there's a little minus hiding on my TCNE label there. So I think it should be pretty good. I mean, Michael can perhaps backfill for me again, but you can generate TCNE minus chemically and measure it directly, which is what this measurement is. So that is the state of the ligand in the solid. So the thing that will be different is there's going to be a vanadium here that's hybridizing with this spin component.
Yeah.
But I think...
So I was
I think it should
thinking
be pretty
back to
close.
Michael's comment about the bands being very narrow, so having a large effective mass for
Mhm.
carriers, and then that suggests that you should have very highly localized spin density.
Yes.
But this doesn't look so highly localized on site, but maybe
Well,
it's still...
again, maybe this is just a question of language, but the way I think about this is this whole diagram is the site.
Yeah,
This is the TC&E site.
yeah.
And then we have a vanadium site over here and a vanadium site over here, say. So the question of mobility is how easy is it to get an electron from this vanadium to that vanadium? So I think that's a measure of the bandwidth, and that is hard. But what's easy is getting a spin from this nitrogen to that nitrogen within the TC&E molecule.
Okay.
So that's sort of what allows it. I sort of put forth the model of thinking of this as an artificial atom, and the way CAD selenide quantum dot people talk about that as an artificial
So
atom.
it's the molecular, if I think of it in a tight binding model, it's basically the molecular level spacing that sets the
Yes,
gap. Okay.
exactly.
Well, thank you.
And let me also comment that the comparison is to something like a 3.5, where the bandwidth is maybe 10 volts, and here it's quite a bit narrower. The bandwidth
Right.
maybe half a volt, but that's tons for communicating. That's certainly plenty,
Okay.
but the mass is still heavy.
Okay. Thanks.
Yeah, I will say, having given talks on this material for, as I said, over 10 years, it's incredibly hard to answer in less than a paragraph any question. It's a little bit of this and a little bit of that, and I think one of the reasons why it's exciting to explore is it just doesn't neatly fit into hardly any of the boxes that we've developed for sort of understanding related categories of materials.
But it's not a unicorn. There are actually other materials
Right.
that are like this. It's a class of materials that's really peculiar.
If you'll pardon a bit of science philosophy, I think something, of necessity, we spend our time looking under the lamppost for our keys, if you're familiar with that anecdote. Right? You lose your keys in the darkness, but you spend your time looking under the lamppost because that's where you can see. That's where we can see, so that's where we spend our time. That's very natural. But it's useful to remind ourselves periodically that there's an enormous amount of phase space for materials out there that we just don't spend time thinking about because we don't have a good reason to, and because we are keeping busy with the things that are more well understood. So that's my more long-winded way of echoing Michael's point, that while it's unusual relative to the things we're used to seeing, it really is, I think, establishing a whole category of materials that should exhibit similar behaviors.
Any final questions? I think people want some coffee. So we'll resume. Thanks. Thanks,
Thank you,
Steve.
everyone.